Hi, I'm Sally Sims, a FAST team rep from Sugar Land Regional Airport. Welcome to this presentation on General Aviation Accident Prevention, a practical guide. This presentation was given at an FAA FAST team webinar on January 20, 2021. Our presenter is Bob Downing. Bob is an ATP-rated pilot, CFI, CFII, MEI, owner of WRD Aviation in Houston, Texas, and has been flying for 39 years and instructing for 25 years. Bob, I'm going to turn the program over to you now.
Thank you, Sally. Here is the topics we'll be covering tonight. And throughout this video there will be links to articles and videos you may want to view after the presentation. So have your phone ready to take a picture of those slides. Well, without further ado, let's begin. Now, on a lark, while talking with a group of my non-pilot friends, I asked them what could be done to reduce small aircraft accidents. Here's what they said. You know, these folks were smarter than I gave them credit for, because a lot of what they said is directly related to the top causes of fatal GA accidents. These are the top 7 causes of fatal accidents. Now, given our time constraints tonight, I won't be able to discuss all of these, so I'm going to focus primarily on these 4. I will, however, touch indirectly on the others. You know, flying is a very complex and dynamic activity, and there's a huge number of factors that need to be considered and dealt with. And things don't always go as planned. The weather forecasts are not always accurate. The unforeseen can happen. These 3 very basic points are arguably the most important things we can do to reduce accidents. And they're true today as they were 50 years ago. Now, it's very easy to say these things, but just saying them does absolutely nothing. Now, as you can see from this clip from the latest Joseph T. Nail report, it shows that 2 out of every 3 accidents are pilot-related. So given that we are the biggest problem, we really need a plan. Something that takes these 3 issues and turns them into something practical that we can use. And one tool to help us accomplish this is a set of standard operating procedures. You know, many GA pilots do not have a formal set of standard operating procedures. They simply make an assessment of whether to fly or not just prior to the flight. Now, while the assessment of the overall risk of a particular flight is a good thing, the problem is without a formal set of SOPs, you may be overlooking relevant risk and flying yourself into a situation you would regret. Now, all the airlines have SOPs, and their safety record is excellent compared to GA's. Simply put, they have SOPs to provide their flight crews with a guide to effectively and safely carry out operations. Why shouldn't we have them? Absolutely no reason I can think of. Now, I do recommend you develop a set of SOPs. Now, what do I mean by SOPs? It's a set of rules that cover making both go, no-go decisions to determine whether you will take off, and another set of in-flight rules once you're airborne. Now, why should you bother doing this? Well, let me turn the question around and ask you, why wouldn't you want a set of rules that make sense, you're comfortable using, and makes you a safer pilot? Now, why would you be a safer pilot? Because you have a formalized set of rules about what you will and won't do. And in flight, if things are not as planned or not going as well, you have a plan of action. Let me show you some examples of what I mean. Now, the following are just a few samples of my IFR rules. And these first 3 you see are examples of some go, no-go rules. Now, a rule can either eliminate a risk or reduce the risk of an accident. And just looking at that first one, I will not fly in an airplane that has just come out of annual or major maintenance until it has been successfully test flown. Let's say that my plane has just come out of some major maintenance. If I had a problem shortly after takeoff, I would much rather be VFR than try to deal with it in an IFR condition situation. So this is a risk reduction rule. Now with the second rule, today many options exist that would allow me to avoid having to fly partial panel if I lost my vacuum pump. Having a backup artificial horizon would completely eliminate that risk. Or that last one. Say I take off on a cross-country flight. What are the chances that I could find a safe place to land if I break out of clouds at 600 feet if I had an engine failure? Not very likely. So this is another example of a risk reduction rule. Now these bottom four are examples of some in-flight rules. And you could apply that same logic we used above and see that these rules either reduce or eliminate the risk of an accident. Now I'm going to pause for a few seconds to let you just look over those. Okay. In my case, several of my SOP rules were hard-won examples that I learned because I experienced situations that caused me to appreciate their value. On this slide, the first one under aircraft, the last one under pilot, and the external pressure ones are all examples of that. Now, what happens if you ignore these risks? Well, in just a minute, I'm going to play 3 snippets of a video that demonstrate this. Before I do, though, I want to say something about external pressures. Get-there-itis has gotten a lot of pilots into serious trouble. It is a powerful psychological motivator that can cause you to push forward in spite of increasing risk. So the next time you find yourself pushing forward, ask yourself, do I have a good out if things deteriorate? Because if the answer is no, don't do it. It's just not worth risking your life for. Now if you want to see the full video, then take a picture of this slide, because at the bottom of the slide you'll see a link to that video. And this accident case study is a very tragic example of what happens if you ignore these risks. In this example I'm about to show you, this pilot ignored every one of these risks that you see on this slide. And you can guess what happened as all 6 people on board met their tragic end.
It's the morning of January 30th, 2009. The Seneca owner-pilot has invited several friends on a flight from the Chicago area to Raleigh-Durham, North Carolina, and Clearwater, Florida. The flight is ready to depart when another pilot notices 5 passengers on board the 6-seat Seneca and expresses concern that the airplane will be overweight. He speaks to the Seneca pilot about this and also urges him to obtain a weather briefing and file a flight plan. But the 2,200-hour non-instrument rated pilot shrugs off the concerns. He assures his friend that he has checked the weight and balance and it is okay. He promises to get a weather briefing and file a flight plan from the air. And so the Seneca 2 takes off VFR for the 558 nautical mile trip to Raleigh. The National Transportation Safety Board reviewed the Seneca's weight and balance. At takeoff, the airplane was more than 300 pounds overweight and 3.4 inches aft of allowable CG. If indeed the pilot calculated the weight and balance as he told his friend, he had to know the aircraft would be operating outside its envelope.
Now 3 hours into the flight, he catches up with a broad weather system stretching from the southwest to the northeast across his route of flight, with ceilings varying from 200 3/4 miles visibility to 1,004 miles visibility, with light to occasional heavy snow. Now as the ceilings lowers, he begins scud runnings. He is in and out of IMC and yet presses on. Shortly thereafter, he declares a mayday, but not due to entering IMC, but low fuel. That was apparently the one thing he couldn't ignore. And he requests a landing at Huntington, West Virginia, which was IFR, reporting ceilings of 1,000 broken, light snow, and 2 miles visibility. Now, this non-instrument rated pilot indicates he is IFR capable and accepts an IFR clearance for the approach to runway 30. After a failed attempt, he's handed off to a surveillance approach controller who gives him a no gyro approach, issuing only headings and altitudes to fly.
The publishment of descent altitude is 1300. Maintain at least 1,300 or above. 1,300. Do not descend below 1,300.
1,300.
Slightly left of course, heading 300.
300.
Turn right in a right turn. Turn right, heading 320. 320. 320 in a right turn. Heading is 310. Roll out heading 300. Now heading is 300. You're now going the wrong way. Heading is 300. Climb to where you have VFR contact with the ground. I see your altitude indicates you're climbing. Seneca 47 Charlie. Seneca 47 Charlie, how do you hear? Seneca 47 Charlie, Huntington approach. If you hear me, I Dan. Seneca 47 Charlie, rate of contact is lost. Seneca 47 Charlie, Huntington approach in the blind. If you hear me, climb immediately. Climb and maintain at least 2,500. Seneca 47 Charlie, if you hear me, I Dan. Correction, 47 Charlie, if you hear me, please respond.
The NTSB speculated that the relatively straight flight paths you see to the south and east were when the pilot became temporarily VFR.
Unfortunately, no amount of analysis can change the outcome of this accident. But even though few of us would think of launching on a 500-mile VFR cross-country over mountains without a pre-flight briefing or a check of the weather en route, we can still take important lessons from this tragedy. Ask yourself, have I ever let external pressure influence me to hurry up, take shortcuts, or press on? Have I ever pushed fuel reserves to the limits? Am I really prepared to turn around or land when the weather does not cooperate? Do I know and respect the limitations of my own piloting skill and experience? Heed the warning signs, act on them, and avoid.
Now, this accident could have been avoided in so many ways. Like, why didn't he use the autopilot? Surely he knew how to use it in heading mode. Was it not working? When the surveillance controller saw he couldn't maintain a consistent heading, he should have asked him to do that. But even with all the mistakes he made, if he would have just turned around upon entering IMC, 6 people would be alive today. Now, as you can see from this graph, VFR into IMC is by far the leading cause of weather accidents. And tragically, more than 8 out of every 10 VFR into IMC accidents are fatal. Now, the AOPA Air Safety Institute says that pilots without an instrument rating typically lose control of the airplane about 180 seconds after entering IMC. Put bluntly, that gives many VFR pilots who enter IMC about 3 minutes to live. Now, if you don't have an instrument rating, you should really consider getting one. But even if an IFR rating is not on the cards for you, when you are doing a training flight, be sure to get some additional training in basic instrument flight to safely get yourself out of this very deadly situation should you encounter it. Now, if you VFR pilots remember nothing else from this presentation, remember this 3 minutes to live rule. And this accident case study we just viewed, it's also a reminder of the fact that while we may be able to get away with reckless or unsafe behavior sometimes, eventually you will pay the piper if you continue doing it. So by thinking about these issues, formalizing them, and adhering to them, you could significantly reduce many of the risks associated with flight. And you'd be much less likely to find yourself in a situation you would regret. So if you've not developed a set of SOPs, give it a shot. You might find it useful and healthy. Now, I have a starter set of SOPs I give to pilots I fly with. And if you'd like a copy, you can send me an email at that address and indicate whether you want the VFR or IFR version. And this is what you'd get with the VFR version. This is what you'd get with the IFR version. And these SOPs cover some 30 to 35 rules to operate by, depending on whether you request a VFR or IFR version. Now, neither of these are a complete set of SOPs, nor are they a recommendation for your SOPs. And it's provided only to spur your thought process as to rules you might want to consider. You should modify them for your level of proficiency, experience, the level of risk you'd want to accept, as well as the types of flying you'll be conducting and the terrain over which you'll be flying. Now, this is an important point, because to have a good set of SOPs, you need to make sure that the rules you create effectively eliminate or reduce a risk, and they are something that you're comfortable adhering to. Because without that, as this slide points out, they're just words on a piece of paper. You need to own these. Now also, you need to understand that you'll probably not have a really good set of rules on your first attempt at this. So don't give up just yet. You may find that, hey, I'm violating this rule, but it's for a very valid reason. And also over time, as your experience and proficiency change, you'll need to modify them. So just think of this as a process and not a one-time event. So give this subject some thought, because SOPs can be a very valuable tool in the arsenal of things you can do to fly more safely, reducing the likelihood of an accident. I want to shift gears now, talk about non-power plant equipment failure. Now this is important because it affects the decisions you make both before and after you take off, and specifically how you're going to aviate, navigate, and communicate. Now, on your instrument check ride, you're required to do one partial panel approach. Once you have your IFR rating, however, you're not required to do one ever again, unless, of course, you actually lost your vacuum pump in flight. So while you're legally current, there's a good chance you were not partial panel proficient. Now, here's some information from an article on the difference between turn coordinators and turn and slip indicators. It is not widely understood or appreciated. So just go ahead and read that. Now I pulled this from the NewTek website. And as you can see from that yellow highlighted box, they're basically saying the same thing that that article did. Now here's an accident that highlights those last two slides. Again, if you want to see this video, take a picture of this slide and then Google accident case study, single point failure. It's a good video demonstrating the importance of this issue. And as you can see, that 4,000 hour ATP rated pilot lost vacuum pressure, leaving him with only a turn and bank indicator for attitude reference. Only 3.5 minutes after entering instrument conditions, he lost control, breaking up in flight. I'm going to show a snippet of this video to demonstrate how serious partial panel flying can be in real instrument conditions. and to discuss a simple way this very tragic accident could have been avoided. The point I want to make, though, is not about whether you should have a turn coordinator or a turn and slip indicator. Both can be difficult, if not impossible to use in some circumstances when you're bouncing around in the clouds.
Sometimes in emergency situations, the entire outcome hinges on the pilot's actions in the moment. Think of Sully ditching in the Hudson River, or the crew of United Flight 232, whose quick thinking and never say die attitude saved hundreds of lives in Sioux City, Iowa. In some situations, though, our fate is essentially sealed long before the emergency makes itself known. The loss of November 440 Hotel falls into that category. In one sense, it was entirely avoidable. And yet, for that pilot, on that day, and under those circumstances, a tragic outcome was all too likely. But why? The pilot's proficiency was the most obvious factor. We have no training records, but the ATC radar track, along with the fact that only 3 or 4 minutes elapsed between the aircraft entering IMC and breaking up, make it clear that, whatever the pilot's opinion of his own abilities, he was woefully unprepared to fly the aircraft in a real-life partial panel situation.
Now remember, this guy was no novice. He was a 4,000-hour ATP-rated pilot. And this video is a good example of why you should have a backup artificial horizon. And today, there's a plethora of options out there. There's probably 15 different options that you could choose from. I've just listed 5 of them here. And if cost is an issue, you can opt for something like the top 2. They're both under $1,000. So do you have a backup artificial horizon? If you don't, you certainly should. And this quote Forrest Gump, it's one less thing to worry about. Now, I just came across this product late last year, and it's a very unique and innovative product. Apparently you just take this bomb and you screw it under the bottom of your wing. There's no wires, it's fully self-contained, and it communicates to iOS and Android devices like an iPad or a phone via Wi-Fi. And it's self-charging. If you see this bottom picture here, or a picture at the bottom, you can see these little turbine wheels. So that as you gain airspeed, those wheels spin and it charges the battery automatically. And it's also got an automatic on-off. So that when you turn it's got a vibration monitor on it, so that when you turn the engine on, the unit actually turns on, and when you turn the engine off, the unit shuts down. And it's got a attitude, heading, and reference system, and so it can provide the 6 basic flight instruments, as well as an angle of attack indicator. It's got a heated pitot-static for airspeed and altitude, and it allows split screen mode on devices, on electronic flight bags like ForeFlight and some others, while showing the 6-pack right side by side it. And there's an optional ADS-B in for weather and traffic. And it's also NORSE approved for certified aircraft. Now NORSE stands for Non-Required Safety Enhancing Equipment. Now I am not recommending this, but if you're looking for a backup for all your 6 basic flight instruments and an angle of attack indicator for around $2,000, this would certainly be something worth considering. But I want to talk about these remote-mounted audio panel and transponders. In our not too distant past, we all had a dedicated transponder and audio panel box physically in our panel, and many of us still do. But with today's avionics, these can be remotely mounted, completely out of sight, and controlled by a device like the GTN 750 that you see here in this slide. Now back when all we had was steam gauges, and our only bit of automation was the autopilot, each piece of equipment was completely independent of the other. With today's avionics, that is no longer true. Now here's what I mean by that. I was in an aircraft in early 2020 with dual Garmin 750s training with a pilot. It had a remote-mounted ADS-B transponder and audio panel, both of which could be accessed and controlled by either 750. Now I failed the number one 750, and to our complete surprise, we lost our ability to communicate and transponder control. Well, here's what happened. So when I failed GTN1, all of a sudden I got this big red box over the audio and transponder controls. Since the audio panel was on COM 1 when I failed GTN1, I couldn't switch to COM 2. So we lost the ability to both transmit and receive on the radio. And likewise, we lost the ability to change the squawk code to the lost COM transponder code of 7600. And that also caused the loss of ADS-B. Now the problem was the avionics shop did not configure the failure mode properly. And I've run into other issues like this as well. So it's a good idea to run an avionics failure test on your plane. So with a power cart or with the engine running, methodically go through and fail each piece of avionics. Check for any configuration setup errors, and then check to see what you lose and determine how you will aviate, navigate, and communicate. Now these next few slides show a series of failure tests. I will only go through 3 of these to give you a feel and understanding of what you should be looking for. So in this first one, this plane had a G5 PFD and a G5 HSI. When I failed the G5 PFD, we lost our autopilot because it was directly connected to the G5 PFD. We had to hand fly the airplane using the turn coordinator, ForeFlight and Stratus for attitude. And we used the GTN 750 to navigate and communicate by. Now this one was an all glass panel aircraft. It had no analog instruments in the whole panel. And when I simulated a complete electrical failure by turning off the alternator and battery, absolutely the only thing that worked on this $130,000 panel was that one little box that you see there. So we had to hand fly the aircraft. We had to use Stratus 3 and ForeFlight to navigate by. And we had to communicate on a handheld radio. Now this one was particularly complex. When I failed PFD1, we lost HSI mode on the G5, we lost glide slope on PFD2, and we lost the nav and approach modes on the autopilot. But oddly enough, heading mode still worked on the autopilot. So we were stuck with non-precision approaches only. We had to use PFD and PFD2 and ForeFlight to navigate by, and we used COM2 to communicate. Now, why did we lose the HSI mode on the G5 and the nav and approach modes on the autopilot? Answer: because the G5 used the heading information from an external source, PFD1, which was failed, and the autopilot uses the G5. Alright, question 2. If the heading information was lost due to a failure of PFD1, why did the heading mode still work on the autopilot? Because the heading information was lost, the G5 automatically switched to GPS ground track. So to fly a specific heading, you had to use a compass to compensate for the difference between ground track and heading. Now, imagine if you did already know these 3 things. You think you could have handled them in flight? What if you were IFR? Now this slide here talks about issues similar to that. And below is a link to this YouTube video on automation dependency. And it's rather long, 25 minutes, but it's a good video on the subject. And although it's directed at airline pilots, with the advanced avionics in our aircraft now, his message actually applies to us as well. And what he's talking about is being a pilot and not an automation manager. So if you can find some time, take a look at this video. Just go to YouTube and in the search bar there, type in Warren Vandenberg, Children of the Magenta Line. So the point is, the more glass you have in the cockpit, the more important an avionics failure test becomes. Don't trust that the avionics shop set everything up correctly. Check for any avionics setup configuration errors. And if an avionics component fails, you need to know what you lose and how you will aviate, navigate, and communicate. But even if you don't have any configuration setup errors or have a lot of glass, you do have some glass. So it's still a good idea to know what you lose and how you will aviate, navigate, and communicate when a piece of avionics fails. Okay, I am going to give you some questions to answer. I'll give you some time to think about it, and then let's see if you get the correct answer. So question 1. Loss of control accidents happen most frequently in what phase of flight? Five, 4, 3, 2, 1. Takeoff. As you can see from this graph, 1/3 of all the accidents are due to takeoff, caused during the takeoff phase. And if you combine takeoff, approach, and landing, almost 3 out of every 4 loss of control accidents happen during those phases of flight. You know, loss of control is the #1 cause of fatal GA accidents. And the most common type of loss of control is an aerodynamic stall, by far, as you can see. Now this is where a tool like an angle of attack indicator could be a benefit. And while I haven't talked about angle of attack indicators, these can be useful to help prevent inadvertent stalls, and they can also help with other things like short field landings and the impossible turn. Now this is an excellent video on angle of attack from one of the angle of attack vendors and how to use it in flight. Now, for a given configuration, the airplane's always going to stall at the same angle of attack. And that angle of attack does not change with any of those factors you see there. And I've listed several examples of angle of attack indicators on the bottom. Now, for many of these, the installed out-the-door costs vary between $1,000 and $3,000, depending on what avionics you have and which systems you choose. Okay, so if you were interested, take a picture. Oh, sorry, let me back up. I got ahead of myself. Yep, okay. You start to notice your instruments are displaying erroneous indications. You suspect a static port blockage. What indications will you get on your instruments if you have a static port blockage? All right, I'm going to give you 15, 20 seconds for this one. Five, 4, 3, 2, 1. Answer: airspeed indicator reads inaccurately. The altimeter is going to be constant and your VSI shows 0. Now, if you're interested, take a picture of this slide because I'm not going to go over this, but it does describe in detail what happens to all of the pitot-static instruments if a blockage occurs. And of course the solutions are relatively simple. You can turn on the pitot heat and or open the alternate static source valve. Okay, question 3. Control flight into terrain occurs most frequently in what phase of flight? All right, 15 seconds. 5, 4, 3, 2, 1. Final approach and landing. And if you combine takeoff, descent, and final approach and landing, almost 9 out of every 10 CFIT accidents happen in those phases. Now, CFIT is the second largest cause of fatal GA accidents. And the problem is you've lost situational awareness and you don't realize where you are. Now, I'm seeing a lot of Garmin GTN 750s and 650s in aircraft now. And here's a tip for you. Here is a tip for those of you with a 750 or 650. And this also works, by the way, with G1000s and some of the newer Garmin products like the G500 and 600. In order to see terrain in detail on the map page, where you will most likely be, you need to turn on the terrain option using the menu button, or on the G1000 the Maps Off key. Now, since many pilots have NextRad turned on so they can see the weather, just be aware that terrain, NextRad, and radar are mutually exclusive options. Only one of those can be on at a time. So if weather is not an issue, you might want to consider turning terrain on for both takeoff and when you start your descent to the destination, since that's where 9 out of every 10 CFIT accidents happen. Now, I do this in mountainous or hilly terrain or at airports at night. And the reason I do is because my experience with the Garmin simulators is that the speeds general aviation aircraft fly at, you get the terrain ahead pull-up warning somewhere between 1 and 3 nautical miles from the terrain. And that's just not a lot of time to react to a potential CFIT threat. So if you get one of these pop-up warnings, your immediate response should be to go to full power, gear and flaps up, and climb at VX. Because if you hesitate at all, the outcome will most probably not be good. Now, I also like doing this because if I just go to the dedicated terrain page on the 750, I lose the approach chart overlay and all of the user fields like distance, next waypoint, ground speed, etc. that you see on this slide, on this second picture. Now, some pilots don't like to do this for takeoff because you will see a red background until you're 100 feet AGL, and then a yellow background until you're 1,000 feet AGL. But to me, it just indicates why I need to keep a good climb rate. You decide, though. Now, I'm going to play a short video to demonstrate what I'm talking about. So hang on, bear with me for a second. So here I am at Grand Junction, Colorado, and the elevation of Grand Junction is 4,860 feet. And so you can see I have the red background screen. Now the good news is I am not looking at the screen during takeoff. My eyes are outside the cockpit, so I really don't even notice this red background screen. In just a second, I'm about to get airborne here. Now you see the yellow sweeping up, so I'm now more than 100 feet AGL. Again, I'm not looking outside yet. I'm not looking inside, I mean. I'm going to speed this up. Now you can see now that I see the big picture. You see the gold creeping in? That's good. When it hits the airplane, that means I'm more than 1,000 foot above the ground level. Now, so being a not wanting to die, I'm going to turn away from the terrain. There we go. Now, just for the demonstration, I'm going to turn back to the terrain.
Terrain.
All right, now notice I just got a terrain ahead warning. Now, the reason this warning popped up at 7.5 miles instead of 1.3 is because on the simulator I was going 450 knots. I was going 450 knots to keep the size of the video down. But at 450 knots, that's 7.5 nautical miles per minute. And since I was about 3.5 nautical miles from that warning, that yellow dot, that would give me only 30 seconds to clear that terrain, with even higher terrain just ahead. But at the speeds typical GA aircraft fly at, that pop-up warning would have shown up at 1.1 to 3 nautical miles. And I'm going to show you that in just a second. There we go. That's what it would look like. And once again, since that red warning, and you see it now says terrain ahead, pull up, because I've got a red dot on the screen, I'm going to have somewhere between 30 seconds and a minute. In this case, more like about 40 seconds to clear that red dot.
Pull up.
Now, I'm turning away from the terrain.
Ahead. Pull up. Terrain ahead. Pull up. Terrain ahead. Pull up. Terrain ahead. Pull up.
Now I'm safe. Here we go. That's what I was looking for. So you can see there's a stark difference with the terrain on and with the terrain off. So you should give this some thought. Also, you need to note that if the map detail is not set to at least this level, you're going to lose the towers seeing only the terrain. Now, if you don't have one of these newer Garmin boxes, you can, of course, as I'm sure some of you, if not many of you, are aware, can use ForeFlight Synthetic Vision, Garmin Pilot Synthetic Vision, and Terrain Alerts. And to get Synthetic Vision and Terrain Alerts, you need to have ForeFlight Pro or Garmin Pilot's Premium subscription. And ForeFlight Pro is costs you another $100 per year, and Garmin's another $80 per year. And of course, if you want the attitude information for synthetic vision, you also need a compatible AHRS device like the Stratus. Now, ForeFlight also has this thing they call Profile View, which is useful. It can give you a nice long-range picture of any hazards as your present route is going to take you through. Okay, question 4. You're en route to your destination. You listen to the ATIS and the airport is below I-4 minimums for every approach. What ceilings must exist at your alternate to fly that approach? All right, I'll give you 15 seconds. Five, 4, 3, 2, 1. The minimums. The difference, of course, is that you're in flight. And the 802 for non-precision approaches and 602 for precision approaches were only for planning purposes. But since you're in flight, you only have to meet the minimums for that approach. That's your alternate. Okay, question 5. What is the first step in recovering from a tailplane stall? I'm going to give you 15 seconds. 5, 4, 3, 2, 1. Pitch up. The first step is to pitch up, and actually a better description would be to pull back on the yoke. Then reduce the flaps and maintain a reduced power. It's pretty much, of course, the opposite of a wing stall. Now, NASA did a lot of research on this subject, both in the wind tunnel, and actually equipped a Twin Otter to test it in flight. If you want to see the full video, Google that link, NASA tailplane icing video. Now when I play this video snippet, note the buffeting of the control yoke, which indicates the incipient stall. And when the actual stall occurs, you're going to see the pilot reduce power, pull back on the yoke, and call for flaps up. Now, during this in-flight test, the flight profile did not actually call for stalling, but that is what happened. And you can tell that the pilot had quite enough of this, because you will hear him say, "That's about as far as we're ever going to go."
Induced a tailplane stall, and the corrective actions they took.
We're starting to get some very relatively high control forces. Oops, I got the speed down.
Full, all standing up, laying back down.
Very, very hard to control speed and even attitude in the airplane. Force is going up as high as probably around 80 pounds randomly, and I can't add any more power to it at this point.
Yeah, we've got...
There we are, we have to stop. Flaps up. They're already moving, okay? I started them up as soon as it went over. That's it, good. Good work. Okay.
All right, guys, good job.
That's about as far as we're ever going to go.
So these are the indications of a tailplane stall and the tailplane stall recovery procedures. Now when the stall occurred and the downward force of the horizontal stabilizer was lost, the aircraft immediately pitched down, reaching a 36-degree nose-down pitch attitude before the pilot was able to recover. Now in the full video, it's pointed out that when you see, if you see any signs of ice on the wings, there's a good chance that there's more on the tail. It is a more efficient collector of ice due to the thinner, sharper shape of the stabilizer. Now tailplane stalls are very rare in cruise, as the tailplane is simply nowhere near its critical angle of attack. But when you're landing and deploy flaps, particularly full flaps, that moves the center of lift aft, increasing the tail's angle of attack, significantly increasing the chance of a tailplane stall. So if you were picking up ice, avoid the use of the autopilot as much as practical, and if you get any indications of a tailplane stall, bring your flaps up to the previous position. You may need to reduce power, then make pitch and power changes. Now, most pilots have never received any training on this subject, so I would encourage you to Google these 2 articles on the bottom of this slide. They're the best I found that explains in simple terms tailplane stall aerodynamics, the factors involved, why it happens, and how to avoid it. In that second article on the right, this pilot experienced an incipient tail stall while coming into land in a Cherokee 6. Unfortunately for him, he had been trained, and so he was able to avoid the stall and land safely. Okay, last question. If I were to receive any of the following communications right now, what would it indicate? Well, I'm going to answer that one for you since it's addressed to me. This presentation is about to end because all of them are true. VFR to IMC is deadly. Just don't do it. Remember the 3 minutes to live rule. Even if an IFR rating is not on the cards for you, when you go up for training, practice some basic instrument flying so that if you do find yourself in this situation, you can safely maneuver back to VMC. Now, I wish I could give you some cookbook to tell you how to maintain proficiency, but I can't. It depends on too many variables. So before you go up for training, really think about what you need to work on, and then work with an instructor or practice with a safety pilot to bring those skills to proficiency. You need to be a part of the process and not just a participant. Now, with regard to frequency of flight, if you're not flying as regularly, figure out a way to change that. Because if you can't, you're just going to have to train more frequently. Because maintaining proficiency is absolutely critical to safe flight, and you need both training and frequency of flight to accomplish that. Now, in that starter set of SOPs I discussed earlier, I do have some suggestions for you to consider with regards to frequency of flight and training. Now, I do strongly encourage you to develop a set of SOPs. While this is not a panacea, you will have a practical plan for what you will and won't do, and a plan of action if you find yourself in a situation. I believe you will find it worth your time developing a good set of SOPs, and if you do, and stick to it, you will be a safer pilot. Another very deadly behavior. Remember, this is a very powerful psychological motivator. Don't be a victim of get-there-itis. Absolutely no reason you shouldn't have an backup artificial horizon. Without one, you are leaving yourself open to unnecessary, potentially deadly risk. Now, I have heard some people and read some articles saying you don't need these. And while I do agree they are not absolutely necessary to fly safely, given that loss of control is the #1 cause of fatal GA accidents, and that stalls are the #1 reason for loss of control, I see absolutely no reason they wouldn't be potentially useful and life-saving. Now, since 90% of CFIT accidents happen in takeoff, descent, and landing, this is a very useful way to see terrain hazards in detail on the map, and giving you ample time to react. Now, if you have a problem, you need to know that before you get airborne and get it fixed. Then if you do have an avionics failure in flight, you will be prepared and know how to deal with it, how you will aviate, navigate, and communicate. Now, if we all were to do these relatively simple and practical things, we could significantly reduce the number of fatal GA accidents. So if I can help in any way, feel free to contact me. There's my contact information. I hope this presentation has been useful. Thank you for watching. Have fun. Be safe.